Hi everyone. So we are going to start with the preparation of alcohols. In this series, we'll be discussing various reactions for the preparation of alcohols. Okay, let's just we'll have a overlook of the reactions that we'll be discussing. So we'll be discussing the preparation of alcohols from alkenes, from aldehydes, from alkanes, and from carbonyl compounds. These are the major and main substrates from which alcohols can be prepared from by different reactions. Okay, we'll be discussing all these reactions in the upcoming lectures, and we'll also discuss the mechanism of the most important ones. Okay, we won't discuss the mechanism of all because it is not important to discuss the mechanism for all of them, but we'll be discussing the mechanism of the most important reactions. Okay, and we'll also try to look at the very important and key concepts of these reactions. So we'll be starting with the alkenes, how to prepare the alcohols from alkenes. We have different reactions for it, and here we are discussing the first one, that is the acid catalysis of alkenes. Okay, so by acid catalyzed hydration we can prepare alcohols. How? By reacting the alkenes with water in the presence of an acid. Okay, an acid as a catalyst, and mostly the acid which we use is H2SO4 sulfuric acid. Okay, so this hydration gives the product, that is the alcohol. Okay, and in the net reaction, that is, there is the addition of water across this double bond. Okay, there is addition of H2O across this double bond. That is, one of the carbons of the of the alkene gets the hydrogen and another one gets the hydroxyl ion. Okay, this is the net reaction, and these are the simple examples. Okay, for the of alcohol preparation from alkenes. In all these reactions, we have addition of alkenes with water, and in the presence of acid, the product is the alcohol. Okay, so first of all, we have to understand the mechanism of this reaction, how this reaction goes, what are the different steps that is followed by the reaction. So the mechanism goes in three steps. We have a three-step mechanism for this reaction. The first step is the protonation of alkene. The alkene that we use as a substrate in the reaction, that is protonated. That is, there is the addition of hydrogen to the alkene, to the double bond of the alkene, and in the reaction we get the carbocation as an intermediate. Okay, and this is the electrophilic addition reaction. The acid catalyzed hydration of alkenes is an electrophilic addition reaction. So in the first step, this hydronium ion, the hydronium ion comes from the reaction between water and sulfuric acid. When water and sulfuric acid react, we get H3O positive. This is hydronium ion, and also we call it as, you can also call it as protonated water. Okay, so the first step of the reaction, there is attack of this protonated water, this hydronium ion on the alkene. As a result, this alkene takes the proton from the hydrogen ion, because this is an unstable entity, because water has a positive charge. Sorry, the oxygen of this oxygen has a positive charge on it, and it cannot bear this positive charge, so it is unstable. For the stability, what it does, the proton is taken by the alkene, and the electron pair of this a bond is shifted towards the oxygen. As a result, this becomes stabilized, and we have a carbocation as the intermediate. Carbocation is the intermediate in the first step of the reaction. Okay, this production of carbocation is the intermediate formation in the first step of this reaction. And in the next step, as the carbocation itself is in unstable entity, unstable species, for stabilization it has only one way, that is, it will react with the water. This water is present in plenty of the amount in the reaction system. So the water will attack on this positive charge, and will again get a unstable entity. This is called as oxonium ion. Oxonium ion. And in oxonium ion, again, water, the oxygen has the positive charge. Again, this is unstable. For the stability, it will kick off one of the hydrogens from it, and will take the electron pair of that to become stable, and the product will be the alcohol. In the last step, that is deprotonation, another water molecule from the system will take the proton from this oxonium ion. As a result, the oxygen will be stabilized, and there will be the production of alcohol as a product, and we get the hydronium ion also as the byproduct in the reaction. So this is the simple mechanism of this reaction, but there are some important points. So the example we have taken in this reaction is also the unsymmetrical alkenes. In case of in case of symmetrical alkenes, if we take an example of a symmetrical alkene, for example, we'll take an example. This is a symmetrical alkene. The double bond has on its both sides the same environment. There is one methyl group, there's another methyl group. So this carbon and this carbon is same. But what if we have a unsymmetrical alkene? This is an unsymmetrical alkene. The environment of this carbon is different from this one. So addition of water across the double bond of the symmetrical alkene is very simple process. The hydroxyl ion can attach to this carbon, or this carbon and hydrogen can attach to this carbon, and or this carbon. Both are one and the same things. But for the addition of water across the double bond of an unsymmetrical alkene, the hydroxyl ion has to decide has to decide the position for itself. Okay, to which carbon it is going to attach, that will be decided by this Markovnikov rule. So according to Markovnikov's rule, the hydroxyl ion will attach to the carbon which is most substituted. Okay, as in this case, this carbon is attached to 1, 2 and 3 carbons. So and this carbon is attached to 1 and 2 only. So this is more substituted carbon. So hydroxyl ion will go to this carbon, and product for this will be hydration. Product for this will be like this. Okay, so hydroxyl ion goes to the carbon which is most substituted, and the hydrogen goes to that carbon which is less substituted. Which is less substituted. This is the Markovnikov's rule, and the Markovnikov's rule can be used to just as a shortcut to predict the product of the hydration reaction, but it cannot be used always. Okay, and in the reaction mechanism, in this reaction we get 2 degree and 3 degree alcohols for all the alkenes except for the ethene. The ethene produces the primary alcohol. Okay, ethene produces the primary alcohol. Okay, this will produce the primary alcohol. Rest all the alkenes have will be producing the 2 degree or 3 degree alkenes. Okay, you can see that we have got the primary alcohol in this reaction. In all other alkenes we can't get this product. Okay, so only for the reaction of ethene we get primary, and for other we have secondary and tertiary alcohols. The reaction is also reversible. That is, if the hydration of alkene is the product is alcohol, the dehydration of this alcohol, if we remove this water from the alcohol, we will be getting the alkene back. So this is a reversible. That's what has been written here, although dehydration is the reverse. And the last one, the most important point of the reaction is rearrangement. Most of the questions are asked from this concept. So there is the possibility of rearrangement. Okay, because as we already told that there is the production of carbocation as the intermediate. So when carbocation is the product is the intermediate, then there comes the question of stability. And there when there is question of stability of carbocation, the concept of rearrangement comes into the action. So there can be the rearrangement. We can have a hydride shift, or we can have a methyl shift in the reaction. These concepts will be understood when we take the example. Let's take an example to understand thing. Look, we have an example. This is a terminal alkene. This is an alkene, and we have the reagents for the hydration. The product, if we want to predict the product of this reaction, so we can predict it by Markovnikov's rule. Okay, according to Markovnikov's rule, We know that this is hydration, that is across this double bond one of the hydrogens will be getting the, one of the carbons will be getting the hydrogen, and one of them will be getting the hydroxyl ion. So according to Markovnikov's rule, this is the most substituted carbon and this is less substituted carbon. The carbocation at this position will be generated as that will be 2-degree carbocation, and the carbocation produced at this position will be the primary carbocation. So this is more stable, this carbocation will be more stable than this one. So according to the, if we take the reaction mechanism, then the carbocation will be produced at this position, this carbon will get the hydrogen, and this will be our carbocation. This is 2-degree carbocation. Okay, and according to Markovnikov's rule, the hydroxyl ion group should attach at this position, but that will not be case in this example. Why? Because we know that in the neighborhood of this carbon we have another carbon atom, and that is having a hydride, that's having a hydrogen attached to it. So there is a possibility that if this hydrogen shifts to this position, here will be creation of a carbocation, and the carbocation will be a 3-degree carbocation, and 3-degree carbocation is more stable than 2-degree carbocation. Okay, therefore hydride shift will take place, this hydrogen will go to this position, and as a result we'll be getting a 3-degree carbocation at this position. Okay, and now here will be the attack of hydroxide. Okay, and we'll be getting the product like this will be the product of the reaction. Okay, so we cannot just predict the reaction product by just looking at by applying the Markovnikov's rule. We have to, although in most cases we will predict the reaction product by the Markovnikov's rule, but always that cannot help us. We should know the reaction mechanism, and we should know all the shifts that will be possible for the production of stable carbocation to get the final product. Okay, let's take one more example, similar example. We have an alkene. Okay, this is a cyclic alkene, again hydration is taking place, so we know there will be the production of an alcohol. Okay, so if we see the reaction, how reaction is going, in the first step of the reaction there will be the production of a carbocation. These are two methyl groups, CH3 CH3. Okay, so in this case this carbon and in this carbon are almost same. Okay, that is the, here it will be produced, 2-degree carbocation will be produced at this position and also this position, but the carbocation will be more stabilized at this position because we have methyl groups present in the neighborhood. So the carbocation will be produced at this position and hydrogen will attach at this position, this carbon of the double bond. Okay, now in the next step what is going to be done, this is a 2-degree carbocation. Now we'll look the neighborhood of this carbon. Okay, there is a methyl group, there are two methyl groups. Okay, and there is no hydrogen, so there is a possibility that there will be a shift of this methyl group. This methyl group can shift to this position. Why it will shift? By shifting this methyl group to this position, there will be the production of a 3-degree carbocation that is more stable than 2-degree carbocation. Therefore there will be shift, and we will be getting, this is the methyl that has shifted, and this is another methyl, and here is the positive charge. Now this is a 3-degree carbocation, and 1 comma 2 1 comma 2 methyl shift has taken place, methyl shift. Okay, this is 1 comma 2 methyl shift that has taken place, and we have got the most stable carbocation, and in the final step of the reaction there will be the production of the alcohol. So this will be hydroxyl group, and this is the final product, this is the alcohol that we have obtained. So in the next videos we'll be discussing other reactions for the production of